Now let us talk about pressure. Okay. So, pressure is a special kind of stress. It is also defined as force per unit area. So, let us look at pressure force on a fluid element. Let us take a coordinate system. So, let us say this is x, that is y, and that is z, and let us take a fluid element. So, this has got a length dx in x direction, dy in y direction, and dz in z direction. So, that the volume of this fluid element that we are looking at is dx, dy, dz. And let us say this fluid element is in a given fluid where there is a pressure distribution. So, that means the pressure is changing from one point to another, and let us say pressure is given as a function of x, y, z, comma t. So, pressure is changing at every point as well as in time. Okay. At any given point x, y, z and t, you know what is the pressure. And what you are going to do is, you are going to now calculate what is the pressure exerted on each phase of the fluid. So, let us say we are going to look at this phase. Okay. So, the phase that I have marked with red color, and I want to calculate what is the force on that side. So, I know that on this side of this phase, I can calculate the force because pressure is defined as force per unit area. Therefore, if I want to talk about a force which is acting in the y direction, okay, on the left side of the plane on the left side of the cube is simply going to be, so let me write left, is simply going to be p times. So, dx is one of the sides, dz is another side, p times dx dz. So, that is the force that is going to be acting on this side of the element. Similarly, you can calculate what is the force on the other side, on this side. Okay. This exactly opposite side of the red side that I have marked. Now, we do not know what is the pressure there, but we can, let us say, do a Taylor expansion and write down the pressure there. So, let us say if the pressure here is given by P, then the pressure here can be written as P plus dou P by dou y into dy. Okay. So, that is the simplest approximation that you can do to represent pressure on that side. So, therefore, F y on the right side is given as P plus dou P by dou y into dy times dx dz. And your interest is to calculate what is the net force acting in the y direction, which you will get if you subtract one from the other. So, if your interest is to calculate Fy net, which is the force acting in the y direction, is given as P dx dz minus P plus dou p by dou y into dy into dx dz. P will cancel and you end up with dou p by dou y, minus sign, into dx dy dz. So, that is the force that is arising in the y direction due to a pressure. We can continue, we can do the same thing in x direction as well as in z direction. So, we can do the same exercise and then you find that f x is given as minus dou p by dou x into dx dy dz, f y is equal to minus dou p by dou y into dx dy dz, and f z is equal to minus dou p by dou z into dx dy dz. So, in the given coordinate system, these are the forces that are generated. I want to write force as a vector. So, this is the component of force in x direction. Okay. The second f y is the component of force in y direction, and f z is the component of force in z direction. So, I can write the net force. So, when I am putting a squiggle under f, that means it is a vector, is equal to f x into x cap plus f y into y cap plus f z into z cap, where x cap, y cap and z cap are the unit vectors in each of these directions. So, I can write that as f x is equal to minus dou p by dou x into x cap minus dou p by dou y into y cap minus dou p by dou z into z cap, okay, is given by f. Or I can simply write that as minus grad p. So, what is grad? Grad is nothing but the gradient operator, that is the grad. So, that when grad is acting on some quantity, that is nothing but, I will use a different one, let us say del phi, that means dou phi by dou x in x direction plus dou phi by dou y in the y direction plus dou phi by dou z into z cap. Okay. So, that is the definition of the gradient operator. So, we get f is equal to, sorry, minus grad p, I missed something, times dx dy dz, which is there for this also, and therefore, I get f divided by dx dy dz, which let me represent with a small f, is equal to minus grad p. So, what is this f now? This f is force per unit volume. Okay. So, in other words, what we have said so far is that pressure gradient, okay, differences in pressure leads to a force, or more precisely, gradient on pressure gives rise to a force density. So, force per unit volume or force density. You have shown now that gradient in pressure gives rise to a force density on the fluid element. Okay. So, F is equal to, F is equal to minus grad P, or f x into x cap plus f y into y cap plus f z into z cap in vector notation is equal to minus dou p by dou x into x cap minus dou p by dou y into y cap minus dou p by dou z into z cap. Let us consider a fluid element under gravity and it is static. So, the fluid is not moving, the fluid element is static. The only force then that is acting on the fluid element will come from gravity. Okay. So, in which case you can say that, so we will use the same coordinate system. So, that is your x, that is your y, that is your z, and gravity is acting in the downward direction. So, there is no force that is going to act horizontally. So, f x is equal to 0, f y is equal to 0, but f z is going to be minus rho times g, where rho is the density of the fluid. So, you know that weight, so gravitational force is nothing but weight. Okay. So, the weight is given by mass times g, but here we are going to write mass. So, weight as mass times g, or it can be also written as volume times density times gravity. We are talking about force per unit volume, okay, or in other or force per volume, and that is just going to be rho g. And I have given the minus sign because the minus sign tells you that it is actually acting in the minus z direction, because this is the diagram that you see on the right, that is the coordinate system that we have chosen. Therefore, if f x is equal to 0 would mean that dou p by dou x is equal to 0, or that means that p is not a function of x. If f y is equal to 0, then you get dou p by dou y is equal to 0, or p is not a function of y. Therefore, p is only a function of z. So, that is what this tells you, that minus dou p by dou z is equal to minus rho g, or p is equal to rho g z plus a constant, which is determined by your p is equal to rho g z plus constant. That is the equation of hydrostatic pressure. Let us see where we can use this. Let us look at application of a manometer. So, where do we use manometer? Manometer is used to measure pressure differences between various points. Let us consider a simple case where you have a pipe, and let us say a fluid is flowing in the pipe, and for the fluid to go from the left side to the right side, you need to apply a pressure difference. So, let us say you have applied a pressure P1 here, and let us say the pressure on the other side is P2, and obviously P1 has to be greater than equal to P2 for the fluid to move from left to right. And at some point you wanted to calculate what is the pressure difference between these 2 points. So, the simplest way to do it is that you can connect a manometer. So, let me draw a manometer. I will draw a U-tube manometer. Let us say big manometer, okay, and manometer has a manometric fluid, which let us say is as shown by the shades of that. Okay. So, the fluid inside the pipe has a density of rho 1. Let us say the density of the fluid, of the manometric fluid, is rho m, and there will be a height difference between two limbs in the manometer. Let us call that h. Now, from our previous analysis, we have found that so this manometric fluid right now is a static fluid. Even though there is a fluid that is flowing in the pipe, okay, the manometric fluid is a static fluid, and therefore, the calculations that we just did is applicable for the manometric fluid. So, let us use that fact, and we found that the pressure does not vary in. So, we will choose the same coordinate system. So, x, y, z. Okay. So, pressure can vary only in z direction, because that is the only direction in which gravity is acting, or weight is there to balance your pressure forces. Pressure does not change in x or y direction. So, if I mark, let us say this point as A, and a similar point here at the same elevation as B, then pressure cannot change between A and B. So, that means P A is equal to P B. But I also know that now I can write the pressure A as pressure at this point, which is P 1, plus the pressure that is going to come from this height. Let us call that height H 1. So, P A is nothing but P 1 plus the fluid that is in this part of the manometer is still that of density rho 1 times G times H 1 is equal to the pressure at B is given by P 2, which is the pressure inside the pipe, plus a fluid which is filling this part of the manometer with a density rho 1, and with a density rho 1, and let us call this height H 2. So, is rho 1 G H 2 plus rho m G H. So, this is the force balance, or rather the pressure balance at point A and at point B, and our interest is to calculate what is P 1 minus P 2. So, I will write P 1 minus P 2 is equal to rho m G H plus rho 1 G into H 2 minus H 1. Now, if you look at this is H 1, this height is H and this height is H 2. So, that means you have H plus H 2 is equal to H 1, or H 2 minus H 1 is equal to minus H. So, I will use that rho m G H minus rho 1 G H, or that is equal to rho m minus rho 1 into G H, or simply delta rho into G into H. So, pressure difference between 2 points is given by the difference in density times gravity times the height, okay, and this is the height that we are interested in, and that tells you how you can use a manometer to measure pressure difference between 2 points. In other words, the pressure difference just got translated into a height difference, and height difference is something that you can measure, and from the height difference you can go back and calculate what is the pressure difference. So, this is a nice application of the equation of the hydrostatics that we derived just now.